This webcast talks about how to do superposition of gravitational forces. So any two objects that have mass exert a gravitational force on each other. And so if you have an area where there are multiple large masses, such as in this drawing, every pair of these objects is exerting a gravitational force on each other. So to find the net gravitational force, we will have to add those forces together. We'll have to find the vector sum. And so I'm going to show you a way to do that. So in this problem, I'm in worksheet 7b. In this problem, there are three masses, and they're configured in this arrangement, kind of along a triangle, and it asks us to determine the net gravitational force on mass A. So I'm going to circle that because that's the one that we are going to try to find the total gravitational force on that. And so I'm going to do a force diagram to find the forces on A. And so I'll just do that right over here. So I'm going to take each pair of objects one at a time. So first, let's look at the at what force mass B is exerting on mass A. So remember that the gravitational force is always an attractive force. It tries to pull the two objects closer together. So object B here is going to try to pull mass A closer to it. And so if A were to move closer to B, it would move vertically down. So I'm going to put an arrow here to represent the force that's the gravitational force that's being exerted on object A by object B. Okay, and then I've got an object over here, mass C, and it is diagonally down and to the right, away from mass A. And so so mass C is going to try to pull A closer to it, and so it's going to try to make A move in this direction. So here would be the gravitational force on object A by object C. Okay, so these are the two forces that we need to add. And, you know, I'm going to need to come up with the components of this force that is at an angle so that I can add them up. And I'm going to, and you know, we have done this before, but I'm going to do this in a slightly different way because it would make it easy to organize if we had multiple forces. Okay, so I'm going to need to understand the angle that each of these forces is acting in. And remember, we need the angles in standard position. So I start on the positive x-axis and rotate counterclockwise until I reach the vector. So for the force that B is exerting on A, that angle is 270 degrees. Let me use a different color. And then I also need to find the angle in standard position of the force that C is applying to A. And let's see, this doesn't look like a typical, or you know, one of the common right triangles, so I may have to calculate this angle here. So I do know the length of the side that's opposite it, and I know the length of the side that is adjacent to it. So I could find, if I just call this theta, I can find theta because the tangent of theta would be the opposite side, 4200, divided by the adjacent side. And since I want to actually find theta itself, I'm going to take the inverse tan, or the arctan, of both sides. So if I do the arctan of 4200 divided by 9700, I can find that angle. So let's do that. So I've got arctan of 4200 divided by 9700. So this angle is 23.41 degrees. That's this angle here, right? 23.41 degrees. And so if I take that away from 360, that gives me the angle in standard position. It's 336.59 degrees. Okay, so now I know the angle in standard position of both of these forces. So I'm going to set up a little table here, and I'm going to find the magnitude and the angle for each one of these forces so that I can then break it into its x and y components. Okay, so I'm starting with the force due to object B, and that's at an angle of 270 degrees. And then my force due to object C is 336.59 degrees. Okay. To find the magnitude, I'm going to take the universal gravitational constant times mass of A times mass of B divided by the distance between A and B squared. Okay, so that should be easy enough for this one because they give me the mass of A. It is 4.4 e to the 8th kilograms. Mass B is 7.3 e to the 10th kilograms, and they gave me the distance. It's 4,200. That's kilometers, so I need to convert that to meters, and then I'm going to square that. Okay, so we will calculate that. So G times 4.4 e to the 8th times 7.3 e to the 10th, and divide by 4,200 kilometers converted to meters squared, and I get 1.215 times 10 to the negative 4th newtons. Okay, so if I multiply that times the cosine of the angle, I'm going to get my x component, and if I multiply it by the sine of the angle in standard position, I get the y component. I might not even need to do that for this one. I can see here that the gravitational force that's being exerted on A by B points vertically down. It's on the y-axis. It is a y component force, right? But it's pointing in the negative direction. So if I just add a negative sign, I have that. There is no x component of this force because it lies on the y-axis. Okay, this is going to be a little more complicated for the other force because I need to find the distance between mass A and mass C. So I need to find the hypotenuse of this triangle, and so that's going to be the square root of 4,200 squared plus 9,700 squared, just Pythagorean theorem. And so that is 10,570 kilometers. Okay, so now to find the magnitude of this force, I'm going to take the G times the mass of A times the mass of C divided by the distance between A and C squared. Okay, so the mass of A is still 4.4 e to the 8th. The mass of C is 8.1 e to the 11th. And then this distance is 10,570. That's kilometers, so I multiply by 1,000 to get it in meters. And let's see what this is. And I get 2.128 times 10 to the negative 4th newtons. Now this is at an angle, and so it doesn't lie on either the x or the y axis. So I'm going to take that magnitude and multiply it by the cosine of 336.59, and that gives me the x component, which is 1.953 e to the negative 4th. And then I take that magnitude and multiply it by the sine of the angle, so times sine of 336.59, and that gives me the y component. Notice it's giving me a negative y, and that makes sense, right? Because this force is pointing down in the 4th quadrant. So I should have a positive x and a negative y. So, and the amount of this is 8.454 times 10 to the negative 5th. Okay, so I have broken both of these forces into x and y components, and so the sum, the net gravitational force, is going to be, I'm going to add the x components and I'm going to add the y components. And so when I add 0 plus 1.95, I get 1.953 e to the negative 4th as the x component of this net force. And then when I add these two y components, let's see, I get negative 2.060 e to the negative 4th. So this is the net force, but it is in rectangular notation, where I'm specifying the extent of this net force in the vector in the x and the y directions. I can tell that this the net force is in the 4th quadrant. And I can tell that because I have a positive x and I have a negative y. I believe the problem asks us to find the force as a vector in polar notation. So now that I have the net force vector, I'm just going to convert it to polar notation. So I'm going to find the magnitude by taking the square root of the x component squared plus the y component squared. Okay, so I'm going to take the square root of the x squared plus the y squared. And I get a magnitude of 2.839 e to the negative 4th newtons. And then I need to find the angle of this net force vector, and that's going to be the arctan of the y component, which is negative 2.060 e to the negative 4th, divided by the x vector, which is 1.953 e to the negative 4th. Okay, but the calculator does not understand. I mean, it can't differentiate whether I have a negative x or a negative y. And so I need to make an adjustment because I understand that this vector is in quadrant 4, and so I'm going to add 360 degrees. Okay, because my calculator will give me a negative angle. Okay, so let's take the arctan of these two numbers. So I've got negative 2.060 e to the negative 4 divided by 1.953 e to the negative 4. And when I do that, I get negative 46.5 degrees, but I'm going to add 360 because it's nice to give our angle as a number between 0 and 360. And so it's 313.47 degrees. So I'll write this net force, net gravitational force, in polar notation. It's 2.839 e to the -4th newtons, acting in a direction of 313.47 degrees. And that is the answer that we're looking for.